Okay, so at the previous lecture we proved a useful Fredholm's criterion for linear operators, the so-called Nikolsky-Atkinson criterion, which states that, roughly states that an operator between Banach spaces is Fredholm if and only if it is invertible modulo compact operators. And we deduced several important corollaries. In particular, we proved that the set of Fredholm operators is open, and the index is a locally constant function on this set. And we also proved that the Fredholm's property and the index are stable under compact perturbations. And at the end of the previous lecture, we began to discuss a concrete illustration of this general theory, namely the index theory for Toeplitz separators on the circle. So let's recall some notation from the previous lecture. We denote by bold T the unit circle on the complex plane. So we work with the Hilbert space L2 of T of square integrable functions on T. More exactly, we consider L2 with respect to the canonical measure mu on the circle, which is the normalized length measure. Length measure divided by 2 pi. This space has a classical orthonormal basis, namely the trigonometric basis, denoted by En. So the function En is given by the following simple formula. So this is an orthonormal basis on L2. It's the trigonometric basis. Why is it trigonometric? Well, when we identify the functions on the circle with periodic functions on the line, so this function will be the respective exponent, e to the power I n t, and this is, of course, a combination of sine and cosine functions. So hence the name trigonometric basis. We introduce the Hardy space. The Hardy space on the circle. By definition, this is a closed vector subspace in L2, which consists of those functions on the circle whose negative Fourier coefficients vanish. This is a closed vector subspace of L2. By the way, it's quite important in some, not only in operator theory, but also in complex analysis. And the reason is that each function in the Hardy space can be extended to a holomorphic function in an open disk. We denote by P the orthogonal projection onto the Hardy space. This is the orthogonal projection onto the Hardy space, the so-called Riesz projection. And now we define Toeplitz separators as follows. First of all, for each essentially bounded measurable function f on the circle, we consider the respective multiplication operator, mf, which acts on the L2 space. So this is just the pointwise multiplication by f. So it takes g to fg. And now the Toeplitz separator is the compression of mf onto the Hardy space. By the compression, I mean the following. We restrict mf to the Hardy space. Of course, there is no reason for H2 to be invariant under this operator. So to get an operator which acts from H2 to itself, we simply compose this operator with P. And the resulting operator is denoted by TF. It acts on the hard space, and it is called the Toeplitz operator. The Toeplitz operator with symbol F. From now on, we will be considering only Toeplitz operators with continuous symbols. This is quite sufficient for most applications. So our goal will be to understand when this operator is Fredholm and to give an explicit index formula for this operator. So at the end of the previous lecture, we proved the following result. We proved that if we take each function f to the respective Toeplitz operator, then we get map from the algebra of continuous functions on the circle to the algebra of bounded operators on H2. So this map is not an algebra homomorphism, but it will be a homomorphism after we quotient out the ideal of compact operators. So this quotient algebra is called the Culkin algebra. It is denoted by Q of H2. And so the map which takes each continuous function f to the class of the respective Toeplitz operator is an algebra homomorphism. This map is an algebra homomorphism. Okay, now we're ready to prove the index formula for, we're almost ready to prove the index formula for Toeplitz operators. But before we can do it, let's recall some elementary facts from basic topology. So we introduce some notation. We will be interested in the set of homotopic classes of continuous maps from the circle to the punctured complex plane. And the set will be denoted like this. So this is the set of homotopic classes of continuous maps from the circle to the punctured complex plane. So basically they are loops on the complex plane that avoid 0. So we will need the following simple fact from elementary topology. The fact is that there is a canonical bijection between the set and the set of integers. More exactly, the map is denoted by alpha from let me say it in a slightly different way. So there exists a bijection. There exists a bijection alpha between this set and the integers, which takes the homotopic class of each En, where En is given by this formula, to n for each integer n. This is very closely related, in fact, to the fundamental group of the circle and of the punctured complex plane. But formally, this is not exactly the same, because when we work with the fundamental group of the punctured complex plane, we consider only loops with a fixed base point. And here we consider arbitrary base points. So This is not exactly the fundamental group, but it is it bijectively corresponds to fundamental group. But this set will be more convenient for our purposes. And now we give the following standard definition. We define the winding number of a loop of a continuous function on the circle to the punctured complex plane to be the image of the homotopic class of F under this bijection alpha. So geometrically, this is the number of rotations of the respective loop about 0. Okay, and now we are ready to prove our main result, which gives us a nice index formula for Topless separators. So I claim that for each non-vanishing continuous function f on the circle, the respective Topless separator is Fredholm. Tf is Fredholm. And the index of this separator is minus the winding number of f. By the way, the winding number is also sometimes called the index of the respective curve, of the respective loop. So we see that two different meanings of the word index are related to each other. Well, first of all, let's show that it is Fredholm. To show that it is Fredholm, just look here. So if f is nowhere vanishing, then f is an invertible element in the algebra of continuous functions on the circle. And a unit of algebra morphism takes invertible elements to invertible elements. So the respective element of the Culkin algebra, Tf plus k, is invertible in the Culkin algebra. But we already proved at the previous lecture that this property means precisely that the operator Tf is Fredholm. Tf is Fredholm. Okay, now let's calculate the index. Let's calculate the index. So because alpha is a bijection, we know that the homotopic class of f is the same as the homotopic class of En, where n is the winding number of f. This is exactly because alpha is a bijection. So, in other words, f and En are homotopic as maps from the circle to the punctured complex plane. So we could draw the following picture. This is the interval from 0 to 1. And here we can consider this space of nowhere vanishing continuous functions on the circle. So I claim that there exists a continuous map gamma from here to here, such that gamma of 0 is f, and gamma of 1 is En. In other words, this is a continuous path in the space of all non-very vanishing continuous functions on the circle, which connects f with En. This is nothing but a homotopy between f and En. Okay, let's now continue this picture. So we have the map from here to the set of Fredholm operators on the hard space, which takes f to Tf, and which is also obviously continuous. This one is continuous, and this one is continuous. And finally, we have the index map to the integers, which is also continuous, or equivalently locally constant. So the composition of continuous maps is continuous. So this composed map is also continuous, but a continuous map from the interval to the integers is constant. So it is constant, and so we conclude that so this picture implies that the index of Tf is equal to the index of Ten. And so to complete the proof, we now have to show that this index is equal to minus n. This will be the end of the proof. And show that this is minus n, let's denote by, let's consider left and right shift operators on the little L2 space, TL and TR. It will be convenient to define these operators on the space of all, on the little L2 space on all non-negative integers. So let TL and TR denote the left and right shift operators. We have an obvious unitary isomorphism between this space and the hard space, which corresponds to the trigonometric basis. If we identify this with the hard space, and if we look at the definition of the Toplot separator, we easily see that Tan is unitarily equivalent to Tr to the power n if n is non-negative, and to Tl to the power minus n if n is negative. So in both cases, we conclude that the index of Tn is equal to minus n. The index of this operator is equal to minus n, and the index of this operator is also equal to minus n if n is negative. And this completes the proof. So in fact, this is the most basic example of a Toplot separator. There are many natural generalizations of this notion to higher dimensions in particular. And the spectral theory of Toplot separators is a very elegant and interesting area which is closely related to topology. In fact, already this case shows that there should be some relation with topology. And for Toplot separators on higher dimensional domains, there are also very nice and elegant index formula. Well, the index, if two operators are unitarily equivalent, then their indices are the same, of course.
Yes, but how do we know that they are unitarily equivalent?
I could say that this is a little exercise, but but in fact, I have already almost explained this. We can, the space little L2 also has a natural basis. Let's denote it by, say, E and bar. So En bar is the following sequence where n is on the nth slot and 0 elsewhere. And En is the nth function in the trigonometric basis of the hardest space. So if we consider the isomorphism between the hardest space and the level L2 space, which takes En to En bar for each n, this is a unitary isomorphism because it takes an orthonormal basis to an orthonormal basis. And if we draw the following picture, this is T-En, and this is, for example, Tr to the power n, and n is non-negative, then the diagram commutes. Let's look at the action of Tn on the basis. So Tn is this operator. Men takes Ej to Ej plus n, just a multiplication operator. In this case, there is no need to apply the projection because Ej plus n will be in the same space. This is exactly the action of Tr to the power n to the elements En bar. And so the diagram commutes. And if n is negative, let's draw the respective picture once again. If n is negative, then I claim that this diagram commutes. And again, to see that it is commutative, we have to look at the action of Tn to the basis, to the vectors Ej. So if n is smaller than j, then this operator takes, the multiplication operator takes Ej to Ej minus n, which will be still in the hardest space if j is bigger than n. So there is no need to apply the projection. It goes to Ej minus n. And this is precisely the way Tl to the power minus n acts on Ej bar. And if j is smaller than n, then this operator takes Ej to 0 because Ej minus n will be in the orthogonal complement of the hardest space. So P takes it to 0. And so the Toeplitz operator Tn takes Ej to 0 if the absolute value of n is bigger than j. And this operator also takes Ej bar to 0. So we see that the action on the basis, the action of this operator on the basis Ej is the same as the action of this operator to the basis Ej bar. And so the diagram is commutative. The diagram is commutative, so the operators are unitarily equivalent and their indices are the same. Okay, that's all I wanted to tell you about Fredholm operators. And our next goal will be to discuss the basics of topological vector spaces. The theory of topological vector spaces is a large area, which is closely related to some neighboring fields of mathematics and has numerous applications, especially in the theory of distributions, in mathematical physics, and in complex analytic geometry. Well, it's not my goal to discuss this theory in detail. We'll discuss only some basic stuff about topological vector spaces. And we will see later that the language of topological vector spaces is also very convenient in classical functional analysis, in particular in spectral theory of linear operators on a Hilbert space. So even if we, as I said before, our main goal of this course is to prove the spectral theorem for normal operators on a Hilbert space. And we will see that to prove this result, it will be very convenient to use the language of topological vector spaces. So this is one of the reasons that we consider topological vector spaces in our course. But of course, there are many other reasons. This is just an important and interesting area of functional analysis with many applications. Okay, so as usual, our base field will be either the field of real numbers or the field of complex numbers. I will give the following definition. Topological vector space is a pair consisting of a vector space X and a topology 2 on X. So it is a topological space. And the topology should be compatible with the algebraic structure on X. So, namely, the operations, the plus operation, and the multiplication by scalars should be continuous for this topology. Well, clearly topological, well, first of all, an obvious example which comes to mind, the first example which comes to mind is a normed space. A normed space is a topological vector space in a natural way. Well, in fact, it's a little exercise, but it's quite easy to show that in a normed space, these operations are continuous. And of course, there are many other examples which will be discussed fairly soon. Obviously, topological vector spaces form a category. So the morphisms are just continuous linear maps. So we will use the following notation. Here we have two topological vector spaces X and Y. Then we denote by script L of xy the set of all continuous linear operators from X to Y. So we have the following simple result about linear operators. Now, first of all, a linear operator between topological vector spaces, a linear operator T, is continuous, even only if it is continuous at 0. And in fact, we can easily replace 0 by any other point of X. And second, the set of continuous linear operators is not just a set. This is a vector subspace in the space of all linear operators from X to Y. Well, the proof is a simple exercise for you. In fact, the axioms of a topological vector space imply that the topology on such a space is shift invariant. And this really implies our proposition. Well, general topological vector spaces are in fact two general objects to be interesting. We'll be interested in a special class of topological vector spaces. And before we define them, let's introduce some terminology. So let's suppose that X is a vector space over the same field, K, or the field of real or complex numbers. So at this point, we don't assume that X is equipped with a topology. So at this point, X is just a vector space. And we recall the following definition. A function P on X and non-negative function P is called a seminorm. If it satisfies the following conditions. First of all, it satisfies the triangle inequality. That is, it is subadditive. And second, it is homogeneous in the following sense. In other words, the only difference between a norm and a seminorm is that a seminorm is allowed to vanish on non-zero elements. If P of X is strictly positive for each non-zero X, then P is just a norm. And let's also introduce the following notation. If little x is an element in our space and epsilon is a positive number and P is a seminorm, then we denote by U P epsilon of X the following set. It's the set of all Y satisfying the following inequality. So in a sense, this is an open ball. Open ball in X. So I put the quotation marks here because our space X is not equipped with any topology at this point. But we will see soon that after we equip X with a certain topology, it will be open in the usual sense. Okay, now we give the following definition. We define a polynormed space. Polynormed space to be a pair XP, where X is a vector space, and P is a family of seminorms on X. So a polynorm space is a vector space together with a family of seminorms. Each polynorm space has a standard topology defined as follows. We define the topology on X generated by P to be the topology that's denoted by tau of P with the following subbase. With a subbase consisting of all open balls, U, P, epsilon of X, where P, little p runs over our family big P, epsilon runs over positive numbers, and little x runs over our space. So in other words, so this is the subbase of the topology. So if we add all finite intersections to this family, we get a base. And so a subset of X is open if and only if it is it can be written as a union of finite intersections of open balls. So each polynomial space becomes a topological space. So now it's a topological space and it's a vector space. So we have a natural question. Is it a topological vector space? And the answer is yes. I have the following proposition. If we start with a polynomial space, then X equipped with the topology generated by P becomes a topological vector space. So we have to prove the continuity of the algebraic operations on X for this topology. This can be done directly, but in my view, it will be more elegant if we reduce everything to norm spaces, or more exactly to semi-norm spaces. So I'm assuming we know this result for norm spaces. We know that this is true for norm spaces. And in fact, the same argument shows that this result is true for semi-norm spaces. The proof is absolutely similar. And now we reduce the general case, the case of an arbitrary polynomial space, to the case of semi-norm spaces. We do it in the following way. For each semi-norm little p from our family, we denote by xp the space X equipped with only one semi-norm little p. So this is a semi-norm space. So we forget about all other semi-norms from our family. We keep only one of them. So this is semi-norm space. We have a canonical map, let's denote it by IP from X to XP. So we equip X with the respective topology. And IP is, well, set theoretically, IP is the identity map. It takes each element to itself. But formally, this is not the identity map because the topology here and here, the topologies are different. So what can we say about this map? Let's observe that, first of all, it is continuous. Well, this is clear because this topology is generated by open balls corresponding to only to P, and this topology is bigger, it is stronger. It is determined by open balls corresponding to semi-norms to all semi-norms from the family P. So it is clearly continuous. And moreover, if we have an arbitrary topological space Y is an arbitrary topological space, and F is a map from Y to X, then F is continuous for the topology tau of P. If and only if IPF, the composition of IP and F, which acts from Y to XP, is continuous for each P. This is more or less immediate from the definition of our topology. So F is continuous if and only if the pre-image of each ball of this form is open on Y. But this means exactly that for each P, for each P, F is continuous as a map from X or from Y to XP. Or more exactly, this composition is continuous. So these properties, in fact, mean that the topology on X generated by P is the initial topology generated by the family of maps IP. And now we can easily prove the continuity of algebraic operations in X. For example, suppose that we want to prove that that the multiplication by scalars is continuous. So we can just draw the following commutative diagram. This is the map whose continuity we want to prove. We want to prove that this map is continuous. So here we have a similar map for the space XP. That's denoted by mu p. Here we have the map IP. And here we have the product of the identity map on K and IP. The diagram is obviously commutative. Now, to show that mu is continuous, we have to show that this composition is continuous. But this composition is equal to this composition, and this one is continuous because IP and mu p are continuous. So this diagram implies that mu is continuous. And similarly, we can prove that the plus operation on X is continuous. And this completes the proof. So now we see that each polynomial space becomes a topological vector space with respect to the topology generated by the family of seminorms P. And it is exactly this class of topological vector spaces that we will be interested in. So we will be interested in those topological vector spaces whose topology can be determined by a family of seminorms. Our next goal will be to give a geometric characterization of such spaces within the class of all topological vector spaces. So to begin with, let's recall some terminology from general topology. Suppose that X is a topological space, and little x is a point in X. And suppose we have a family, say beta x, a family of neighborhoods of X. We say that this family is a base of neighborhoods of X, or briefly, just a base at the point X, if the following condition holds for each neighborhood U of X, there is a neighborhood V in this family, which is contained in U. So this notion shouldn't be confused with the notion of a base of the whole topology. In particular, we don't require here that U is a union of neighborhoods from beta. This is not the case in general. So a typical example is, if, for example, if X is a metric space, then we consider the family of all open balls centered at X. And this is a base of neighborhoods. If you take any neighborhood of a point and a metric space, we can always find a ball centered at X contained in this bigger neighborhood. A more general notion is the notion of a subbase of neighborhoods. So if we have a family, say sigma x of neighborhoods of X, we say that sigma x is a subbase of neighborhoods of X, or briefly just a subbase at X. if finite intersections of sets from sigma x form a base at x. The family of all finite intersections is a base at x. Okay, let's now come back to polynomial spaces. Let's introduce some more notation. Suppose that x, together with a family of seminorms P, is a polynomial space. So if we have finitely many seminorms from P, say P1 to Pn, and a positive number epsilon, we denote by the following symbol. The intersection of the open balls, UPI epsilon, centered at x. So explicitly, this is the set of all y in our space, such that pi of y minus x is less than epsilon for each I from 1 to n. And we have the following simple result. Position. First of all, the family of all open balls centered at x, up epsilon of x, where p runs over big P and epsilon runs over positive integers, or positive real numbers. So this is a subbase of neighborhoods of x. A subbase at x. And second, if we consider all sets of this form, where little x is fixed, so here P1 to Pn are seminorms from big P, and again epsilon is a positive number. So the family of all these sets is a base at x. The proof is a simple exercise for you. This is almost automatic from the definition, but formally it is not immediate from the definition, but this is very easy. Why is it not immediate from the definition? If we formally look at the definition of a subbase of neighborhoods of x, and if we look at the definition of our topology, then we can easily see that to get a subbase of neighborhoods of x, we must take finite intersections of arbitrary open balls containing x, but not necessarily centered at x. Not necessarily centered at x. But the triangle inequality easily implies that each such finite intersection actually contains an open ball centered at x. So if we use the triangle inequality, we easily get this result. Okay. Okay, now let's introduce the following geometric notion, or rather a geometric condition on a topological vector space. We say that a topological vector space X is locally convex. Locally convex if X has a base of neighborhoods of 0 consisting of convex sets. convex sets. Of course, we can easily replace here 0 by an arbitrary point. Again, for the obvious reason that the topology on X is shift invariant. And briefly, a locally convex space, is a short form for locally convex topological vector space. This is just a standard terminology. When we say locally convex space, we mean locally convex topological vector space. Here is an obvious example. If we start with a polynomial space, xp, we already know that X becomes a topological vector space for the topology generated by P. But it's almost immediate from the previous proposition that this is a locally convex space. Let's abbreviate locally convex space as LCS. Is an LCS. This is immediate from this proposition, because clearly the triangle inequality implies that each open ball is convex. And of course, a finite an arbitrary intersection of convex sets is convex. So if we put 0 here, then we get a base of convex neighborhoods of 0. But in fact, the converse is also true. So we have the following theorem. A topological vector space X with the topology tau is locally convex, even only if tau is generated by a family of seminorms. There is a family of seminorms P on X such that tau is generated by P. Well, I'll give you a sketch of proof. So I'll leave some easy details of the proof as exercises for you. Of course, we have to prove the left-right implication. The opposite implication is clear from the previous example. So suppose we start with a locally convex space, and we want to construct a family of seminorms which generates the original topology. So let's choose a base of convex neighborhoods of 0. Say UI. This base of convex neighborhoods of 0. So as a first step, we modify each neighborhood in this base in such a way that the new neighborhood will be not just convex, but absolutely convex. So let's denote by d bar the closed unit disk. Well, this will be the closed unit disk if the base field is the field of complex numbers. And if we use the field of real numbers, then this is just the closed interval from -1 to 1. And by using the continuity of the multiplication by scalars in our space, we observe that for each I, we can find another neighborhood. There exists a neighborhood, say Vi of 0, such that the product of d bar and Vi is contained in Ui. For each I, for each I, there is neighborhood Vi with this property. This follows from the continuity of multiplication by scalars. And let Wi denote the convex whole of this set. Then it's an easy exercise to show that Wi is also a convex neighborhood of 0. Convex neighborhood of 0. It is obviously contained in Ui. Well, this set is contained in Ui, but Ui is convex, so the convex whole is also contained in Ui. And Wi has the extra property that it is stable under multiplication by our disk. So such sets which are convex and satisfy this condition are called absolutely convex. Wi is absolutely convex. Okay, and now we can construct our family of seminorms. So we define a function pi of x and a negative function by the following formula. Pi of x is the infimum of those non-negative lambda such that x is contained in lambda Wi. By the way, let's observe that this is always, such lambda always exists because the multiplication by numbers by scalars is continuous, and Wi is a neighborhood of 0. So this implies that if lambda is small enough, then x belongs to this set. Sorry, if lambda is big enough, x over lambda will be in Wi. So if lambda is big enough, then 1 over lambda is small enough, and this and we have this inclusion. There is a special name for this function. It is the so-called Minkowski's functional. This is the Minkowski functional of Wi. And now to complete the proof, so the end of the proof is a set of 3 exercises. First of all, Pi is a seminorm. This easily follows from the fact that Wi is absolutely, absolutely convex. Second, the open unit ball centered at 0 for the seminar Pi is precisely Wi. This can be easily deduced from the definition of Pi. And finally, exercise 3, which easily follows from 2, the original topology on X is identical to the topology generated by the family of all these seminorms. And modulo these exercises, this completes the proof. So we see that each polynomial space becomes a locally convex space for the canonical topology generated by a family of seminorms. And conversely, each locally convex space is polynormable in this sense. So its topology can be generated by a family of seminorms. And each such family, of course, there can be many different families generating the same topology. Each such family is called a defining family of seminorms. Each such P is a defining family of seminorms on X. So we see that the relation between polynomial spaces and locally convex spaces is about the same, similar to the relation between metric spaces and metrizable topological spaces. So of course the structure of a polynomial space is essentially richer than the structure of the respective topological vector space, because the same topology can be generated by many different families of seminorms. However, when we work with such spaces, the concrete family of seminorms is not so relevant. What is really relevant is the topology of the space. And probably this is the main reason why the notion of a polynomial space is not so much in use. On the contrary, the notion of a locally convex space is absolutely standard. And so I'll follow the tradition, and I'll never use the notion of a polynomial space anymore. But however, the fact that all locally convex spaces are polynormable in this sense is very important, and I'll constantly use it. Well, probably I should continue here. A nice feature of locally convex spaces is that when we work with such spaces, we have two languages at our disposal. A language of general topology, of neighborhoods and so on, and the language of seminorms. And quite often a topological notion, about some topological statement about a locally convex space can be conveniently interpreted in terms of seminorms, which is quite useful. Let's just look at a couple of illustrations. For example, suppose that we have a locally convex space X, and let's denote by P a defining family of seminorms on X. I claim that this space is Hausdorff. Even only if for each non-zero element in our space, we can find a seminorm in our family such that P of X is strictly positive. Well, indeed, to prove the left-to-right implication, let's observe that if this condition is not satisfied, if it fails, then X belongs to each neighborhood of 0. So otherwise, if this condition fails, then X belongs to each neighborhood of 0. Because if we look at the standard base of neighborhoods of 0 generated by seminorms, we see that X belongs to each such neighborhood. So X is not Hausdorff. X is not Hausdorff. And to prove the right to the right to left implication, well, let's take two distinct points, X and Y, in X. So X is not equal to Y. So Y minus X is non-zero. And by using this condition, we can find a seminorm from our family, a seminorm P, such that P of y minus x, let's denote it by D, is positive. And now the triangle inequality easily implies that the following neighborhoods, open balls of radius d over 2, centered at x and y, are disjoint. And so the space is Hausdorff. Another simple fact which shows the relevance of seminorms. Again, suppose that we have a locally convex space X equipped with a defining family of seminorms P. So I claim that a sequence Xn converges to X for the topology tau of P, if and only if it converges with respect to each seminorm from our family. For each P, P of Xn minus X goes to 0. And the proof is a simple exercise for you. Well, in conclusion, let's look at some concrete examples of locally convex spaces. Example 1. Suppose that X is any set, and let's look at the space of all k-valued functions on X. We denote it by k to the power x for obvious reasons. This space has a canonical locally convex topology generated by the following family of seminorms. So for each point in our set, we define a seminorm indexed by this point by the following simple formula. This is just the absolute value of f of x. So clearly this is a seminorm. And the resulting family of seminorms on k to the power x generates the so-called topology of pointwise convergence. Generates the topology of pointwise convergence. On k to the power x. Why is it so called? Well, if we look at this proposition, we see that a sequence Fn converges to F for this topology, if and only if it converges pointwise. And in fact, it's very easy to show that this topology is nothing but the product topology. The topology of pointwise convergence is nothing but the product topology on k to the power x. The topology of the topological product topology of many copies of the base field. Example 2, let now X be a topological space. So we want to define a locally convex topology on the space of continuous functions. And we do it as follows. For each compact subset K of X, we define a seminorm indexed by K on the space of continuous functions by the following formula. The seminorm evaluated at continuous function f is the supremum of f of x over k. This is finite because f is continuous. And this is easily seen to be a seminorm. So we get a family of seminorms on C of x indexed by compact subsets of x. And this family generates the so-called topology of compact convergence. The topology of compact convergence on C of x. In fact, this is a special case of the compact open topology. If we look again at this proposition, we see that the sequence Fn of continuous functions converges to f in C of x for this topology, even only if it converges uniformly on each compact subset. It converges uniformly on each compact subset k of x. Well, example 3. Oh, and this will be the last one. Example 3. Let's look at the space of smooth functions on a closed interval, a, b. Of course, there is a naive way of make this space into a topological vector space. We can just take the supremum norm, so it will be a normed space. But this is not the right choice, because this norm doesn't reflect the nature of the space. The canonical topology on the space is given as follows. So for each non-negative integer n, we define a seminorm on the space to be the supremum of the nth derivative of f over the interval. So if n is 0, then this is just the usual supremum norm. And if n is positive, then this is a seminorm. And the standard topology on the space of smooth functions on the interval AB is generated by the family of all such seminorms. So if we look once again at this proposition, we see that a sequence fi converges to f for the standard topology on the space, if and only if it converges uniformly with all derivatives. So this is the topology of uniform convergence of all derivatives. Okay, so that's all for today. At the next lecture, we give some more examples of locally convex spaces. And then we prove a useful continuity criterion for a linear operator between locally convex spaces, which generalizes the well-known fact that a linear operator between normed spaces is continuous, even only if it is bounded. Okay, thank you.